Let's recap our work on focal mechanisms and beach balls once again, and the nature of faulting. So first, at the top left, we have strike-slip faulting, where one block slides horizontally past the other block along the fault zone. And this is shown in a focal mechanism by this checkerboard pattern, with one of these nodal planes being the fault zone, either this one or this one. And the only way that can be determined is by looking at the orientation of the fault out on the ground surface. We can see it can either be a north-south fault that we see right here, shown by this nodal plane, or an east-west fault, shown here. Either one can be possible, but we can refine our estimate by looking at the fault zone out on the ground surface. Then we have normal faults. Normal faults showing this cat-eye pattern, however the middle of the cat-eye pattern is not colored in. The edges are colored in. These are where you have the compressional or push arrivals. In white is where you have the pull or dilatational arrivals. Once again, either one of these nodal planes, which separate the quadrants of compression from dilatation, either one can be the fault zone. The only way we can tell the difference is by, once again, going out into the field and examining the distribution of aftershocks to get the orientation of the fault zone. Now, let's move forward to reverse. To reverse is shown here. Once again, now this pattern of the focal mechanism is a cat-eye pattern with dark now being in the middle. So this is the area of compressional arrivals, with dilatational arrivals being on either side, along the margin of our focal sphere. Now, if we look at the potential patterns of faulting, here we have right here, it could be a steep fault, as shown by this nodal plane, or it could be a shallow dipping fault, as shown by this nodal plane. The way to try to isolate which one of these is the true, proper, or most accurate fault is either with the aftershock distribution or going out and seeing the fault out on the Earth's surface. And lastly, shown here, it's kind of a combination of the checkerboard and the cat-eye pattern. When you see this kind of hybrid combination, it means the slip is oblique, meaning that it's partly strike-slip, but partly dip-slip, in other words, vertical motion, either hanging wall up or hanging wall down. But the point is, it's a complicated slip, and it could be either one of either partially strike-slip and partially vertical motion. Well, let's go back and kind of look at our Loma Prieta earthquake once again. As we did already, we used the aftershock pattern and its area to determine, at least help us determine, the average displacement being about 2 meters. We used our seismic moment formula, having gotten the seismic moment for analysis from our seismograms, which we didn't do in this class because it's just a little bit beyond this class, but we did determine the area fault rupture from the aftershock pattern. That's fairly straightforward and easy. And then using the seismic rigidity of 32 gigapascals, we can come up with the average amount of displacement or slip, and it ended up being 2 meters, the example we did earlier in this particular exercise. Then we can examine our focal mechanism, which we see right here. Here is the focal mechanism for the 1989 Loma Prieta earthquake. And you see it's partially a checkerboard, but partially kind of a cat-eye pattern. This says it's oblique slip. It was oblique slip, meaning that part of the slip, in fact 1.2 meters of the slip, was strike slip or horizontal displacement. And 1.6 meters of the slip was reverse slip or hanging wall up. In other words, some vertical motion. So the 1989 Loma Prieta earthquake had a complicated focal mechanism and pattern of slip. Partially right lateral strike slip, and as we'll learn later in this class, is characteristic of the San Andreas Fault, but also it had vertical motion or reverse motion. Indeed, that makes perfect sense, because why do we have the Santa Cruz Mountains? The ground has risen up, and it's probably risen up by multiple of these reverse slip events. In other words, hanging wall moving up. In this case, about 1.6 meters with just the 1989 Loma Prieta earthquake. And there is the fault. So we can choose which one of the nodal planes, and that's the nodal plane that is parallel to the San Andreas Fault right here. So this would be the fault plane on our focal sphere by seeing how it is has the same orientation of the pattern of aftershocks along the San Andreas Fault. And we can examine, and we will examine in Unit 2, the patterns of focal mechanisms around the world along the various plate boundaries. And what do these focal mechanisms say about the type of plate boundary? Whether or not the plates are moving apart, so-called divergent plate boundaries, whether the plates are moving together, so-called convergent plate boundaries, and where plates are moving horizontally, one by another, through strike-slip faulting, or what's called a transform plate boundary. So we'll see this later on in Unit 2 of our class. So what are our conclusions for the 1989 Loma Prieta earthquake? First, here is the epicenter. The epicenter, which was located, if we did the analysis, by the S-P technique. So we have the location. Then we determine the depth by the small p, big P minus big P technique. And in doing so, we could plot out the aftershocks. The aftershocks, which tell us the extent of rupture and the orientation of fault slip from the aftershock locations and the amount of slip when we use the seismic moment. And then we could use our focal mechanisms by plotting the distribution of push arrivals or pull arrivals around our epicenter, and that, when we plot out the focal mechanism, tells us the type of faulting, which in this case is oblique slip faulting, partly strike slip, but partly vertical or thrust motion or reverse motion. And there's the fault plane. So let's summarize. Today, we use an example from California earthquakes, California seismicity. In particular, we examined the 1989 Loma Prieta earthquake as a case study for examining the distribution, the location of the main shock, and the distribution of the aftershocks. And we use that to discuss the hypocenter, the earthquake location at depth, down within the earth, and we want to make sure we distinguish it from the epicenter, the surface projection of that earthquake location. Then we discussed fault rupture and seismic moment, and how we got to that through an analysis of aftershocks, those earthquakes that follow the main shock. Then we went further, finally looking at the type of fault motion that occurred during that earthquake. And we analyzed that fault motion, and we did that through an analysis of focal mechanisms. So if you have any questions, please post them in the Dawn's office discussion area.